Okay, and this is part two. Now, you may have realized that we're working in chapter 14, and this is just a diagram from our textbook, sort of showing us the scenario. And again, we're using circular motion as this sort of platonic object that we can make a shadow of on a screen that looks like oscillation, periodic motion back and forth. So we'll model periodic motion using this rotating ball on a table according to the diagram. And what that means is that we've got a ball moving in circular motion, and the shadow is the x coordinate. And they've got the equation there written for it, a, where a is the radius of that circle, times cosine of theta. And that's where I'll stop sharing the screen for now. I'll come back to another image in a second. Okay, so a little bit more recapping. We've got our circle, radius r, and we've got a thing rotating counterclockwise. The x-axis is here, the shadow, the screen, in other words, on which we're making that shadow. And I've got a couple things marked here. I've got an origin, O, and if we wanted that to be some other coordinate, if you wanted to put the origin somewhere else, we could do that. It would just change the intercept. It'd be fine. We've got the maximum extent of the x coordinate away from the origin. And I guess on the other side, there's a minimum, a negative x coordinate that is as far away from the origin as we can get. And then there's the x coordinate of the shadow as time goes on. We start, let's say, at theta equals 0 on the x-axis. And as we rotate, theta is omega t. And if we borrow the textbook's equation, we know that the x coordinate as a function of time is the radius. I called it r instead of a, times the cosine of theta. But we know, because we've got a thing rotating at angular velocity omega, that the equate the relationship that describes the x coordinate as a function of time is the radius times the cosine of omega t, in other words, the value of theta. If we had started from not theta equals 0, in other words, what if we started from here, theta 0, and then continued rotating past that? Well, okay, we still go through a delta theta according to omega t. We just started somewhere originally. So we go this far after having started from here. And in fact, this is our kinematic formula for rotation. Our theta as a function of time, we wrote back in chapter 9 as the initial plus the constant angular velocity times time. And that's just this formula written again for theta with some initial value to begin with. Okay. If this is going to work as a model for actual periodic motion, then we're going to have to make sure that our model aligns with the reality. And there's two pieces of this puzzle that we have to make sure are equal to what they should be. There's one piece that's relatively clear and another piece that's going to take a little bit of work. We're imagining circular motion of radius r and angular velocity omega. Those are parameters that we're making up. That there is no such circle. Only in our Platonic imagination does that circle exist. Which means if it's going to work, if this sort of imagined thing is going to do a good job of representing horizontal motion back and forth, we better make sure we imagine the right radius and the right angular velocity. Okay. R, that's the nice one. When theta is equal to 0, we're just on the x-axis. And we could draw the radius vector from the center out to that point. That is the largest possible x-coordinate we're ever going to have. We're as far from the center of that circle as possible. So we know that that x-coordinate, when theta is 0, should be the radius. It's a radius away from the center. So when theta is 0, x should be r. But x, our furthest x-coordinate from the origin, we called that x max. So the x max, the largest possible value for the x-coordinate of this oscillating shadow, the oscillating object, is equal to the radius of that circle that we're imagining. So x max is going to have to be, it's going to have to correspond to the radius of our circle. Okay. So I'll make that change. X max cosine omega t plus the initial value. Here, I guess if you wanted to shift it, put the origin someplace else, you might need some constant term to shift the function around the graph. And now that we've written that, there's a piece that I want to remind us about trig functions in general. Every trig function has 4 dials on the front, like a stereo, or like an old CRT computer monitor, like this one. Every trigonometric function, sinusoidal function, has 4 buttons in it, 4 dials that are like the 4 buttons on this computer monitor. Let me zoom in a little bit more here. These buttons talk about the horizontal shift of the screen on the actual, in the tube, the width of the screen, the vertical positioning of the screen, and the vertical size of the screen. And those 4 buttons correspond to the 4 parameters, the dials on the front of each trigonometric function radio. There are 4, and you think back to pre-calculus to remind us how they work. I'm going to skip away from the screen. Every trig function, A cosine B, so let's make this y of x, bx plus c plus d. Every trigonometric sinusoidal function has those 4 parameters. And what are their jobs? A is the parameter that handles the vertical size of the picture, and we give that parameter a name. We call it amplitude. D, just kind of working from the outside in, D is the parameter that handles the vertical positioning of this function on the xy plane. Vertical position. And it's, it represents the center line of that cosine function. If we graphed it, the center line would be the line y equals d. The parameters inside the argument of the trig function, parameter b handles the horizontal scaling, horizontal size of the picture. It changes the space, the horizontal space on the x space that the function needs to take up one full period. So, do you remember how to find the period of a trig function from its formula? It's 2 pi over this parameter, 2 pi over b, unless you're talking about tangent or cotangent, then it's just pi. But if it's sine or cosine or secant or cosecant, 2 pi over b. The last parameter is c, handles the phase shift. That handles the, we're going to call it the phase shift, but it handles the horizontal position. We're going to call the phase shift negative c over b. Sorry about that. Scrunched writing down there. Oops. When you first learned this back in pre-calculus, your professor might have used a minus sign here in the general form of the trigonometric function, and that's fine. If the minus sign lives here, it doesn't live here. It lives one place or the other, but not both. So if you write the plus sign here, then the minus sign gets to live here. Okay, so that's that, and that means that what we just wrote, x max cosine omega t, that means that x max is the amplitude, apparently, of this trigonometric function. That the wherever it is we put the origin, let's make that the center line of the function, and that omega. All right, well, I guess the period of this function is 2 pi over omega, and the phase shift has to do with the initial angle and omega. But then we have language to talk about the different parameters that live in this equation for the x position as a function of time. Okay. So far, so good? I gotta erase this now. Let's keep the origin in the middle here so that we don't need that plus x0, just to keep things kind of nice. And this is our sort of model prototype for the horizontal coordinate, the x coordinate of this object in horizontal oscillation. We still are not sure what omega is really, like r, the radius of the circle that we're imagining, that corresponds to the maximum distance from the equilibrium of that oscillating mass, but we're still not sure what omega represents. I guess that's okay for now. I just want to see if this is actually going to work at all. Newton's second law should still hold, even though we're imagining stuff. So in the horizontal case, there's no gravity to worry about. We just have the stretched spring. If the x coordinate is positive, then it's going to pull us back the other way. if the x coordinate is negative, then it's going to negative x minus, it's going to push us positive. And ma is going to be the other side of Newton's second law. And we know that the acceleration is the second derivative of the position. So that's fine. This is a second order differential equation, and that's kind of weird. But that's where we get, that's where we kind of stopped. But now we have a prototype. We've got a thing that is the x position as a function of time, a thing that we can take happily two derivatives of and plug it in here. Does it actually work? If this prototype satisfies Newton's second law, then the thing that we're imagining, this Platonic circle, rotating somewhere in Plato space, that is capable of solving Newton's second law to describe oscillation. Okay. Fine. So negative kx equals m. Let's take two derivatives of this with respect to time. All right. Well, let's do this in order. We'll take one derivative and then leave one derivative to take still. So if we take a derivative of this, now x max is just a coefficient. So we need the derivative of cosine, which is negative sine x max, negative sine. Exponential functions and trig functions keep their arguments. The argument stays the same. But we do still need the chain rule. We took the derivative of cosine, but then we still need the derivative of its argument with respect to time, and the derivative there gets us a factor of omega. We still need to take another derivative, but for now, take a second, make sure that that derivative goes like it's supposed to. Cosine's derivatives minus sine, keep the argument, and then, okay. All right, so now we need another derivative. Again, x max is just a coefficient. The derivative of sine is cosine, so we've got a minus sign there left over. Negative kx equals m. So we'll get a negative sign from here, and x max, because it's just a coefficient, and the omega that we've got there, times the derivative of sine, which is cosine, keep the argument. And then again, we need the chain rule here. We're going to get another factor of omega multiplied. Let me make it omega squared here. How does this help us? Okay, so the right-hand side is great, I suppose. Let's see, wait, x, like the x position as a function of time, which we know, we've got a formula for that. So let me just, all right, gonna have to write small, negative k times cosine omega t plus equals m times negative x max omega squared cosine omega t plus theta 0. Close. Wait a minute. Do you all see what I'm seeing? We've got an x max on both sides. We've got a minus sign on both sides. Let's divide both sides by negative x max. we've got a cosine omega t plus theta 0 on both sides. Let's divide by that. And we have, let's see, we got k, oh, just k, all right, equals m omega squared. This equation relates the parameters of the spring and the mass hanging on it of our actual physically real oscillation to the angular velocity of the imaginary circular motion that we're thinking of in Plato space up there somewhere. This is what we need. In order for this circle, in order for this circular motion to be a Platonic object that can make the oscillation shadow actually line up with our experience, omega, the omega that we imagine, must be k over m. If the omega that we make up isn't actually the square root of k over m, then this isn't a good model for the oscillation that we're trying to describe. But if it is, then this prototype is capable of solving Newton's second law for the oscillatory situation of a mass on a horizontal spring. So as long as we imagine the right Platonic circle, in other words, where omega is square root k over m, and where the radius of that circle is the maximum displacement from equilibrium. Ooh, that's the trigonometric function dial. That's the coefficient. That's the amplitude. So the distance from equilibrium, as long as the radius of our circle is that, and the angular velocity of the rotation is that, then we're golden. We've got a circular motion derived idea that represents oscillation in one dimension. Wow. All right, cool. What else? What can we say about this? So I got to erase some of this so that there's room to say some other stuff. If we know the position as a function of time, then we've got the whole story. We can find the velocity as a function of time. We can find the acceleration as a function of time. We can take a derivative of this prototype. So the velocity as a function of time, we actually took it a minute ago. We already know what it is. It's negative x max sine of omega t plus theta 0 times omega from the chain rule. Okay, let's interpret that a little bit. Let's say let's say theta 0 is 0, and we start from the x-axis in our rotation here. As we rotate through, let's say that theta, omega t, gets to be 90 degrees. So we're right here at the top of our circle. At that instant, we know the velocity of this rotating object. It's only tangent to the circle. The velocity is always tangent to the circle. But in this case, we know that it is entirely in the x direction. At any other time, the velocity might have a tangent that has some x component and some y component, but at the top, we know that it only has an x component directed to the left. And if omega t plus theta 0 is 90 degrees, then the sine of 90 degrees is 1. And what we just found is the maximum speed that we're going to have on our way back through the origin is negative x max times 1 omega. Now, as we go around the circle, we get to 3 pi over 2, we're headed back to the right. So our V max, I guess, you know, it could be positive or negative depending which way we're going. So, you know, I guess there's that, but in terms of magnitudes, but the thing is, this isn't a surprise at all. Not now that I'm looking at it, because this looks like omega, and x max is the radius of that circular motion. So that's this. We're just saying this. But of course, it's that. I mean, it has to be. And we know what it is because as long as we keep omega equal to that the value that corresponds to actual, you know, reality, x max, we know that omega is the square root of k over n. So we can talk about the maximum speed in terms of how far we pull the mass away from equilibrium and the stiffness and how much mass it has. Wow. All right. Suppose now we've got a mass oscillating along the x-axis, and if you tell me what time it is, I can tell you what the velocity is. But what if I don't want to have to know what time it is? What if all we want to be able to say is, all right, we are here at x. What's our velocity? Never mind what time it is, because we're going to be there at infinitely many times as we go around and round and round in the circle, as we go back and forth and back and forth and back and forth. We're going to get to that point over and over and over again at infinitely many times, a period apart. But it's always the same point in space. So maybe a function of time isn't what I'd like. Maybe a function of space is better for some application. But the sine of this angle, the sine of the angle that describes where we are around the circle, that's the y coordinate, right? Let me just draw this again really quick. We got our circle, we got here's our argument, omega t plus theta 0. The x coordinate is what we've been talking about, and the sine of that is going to be related to the hypotenuse and the vertical piece, the vertical component. So, okay, wait a minute. The sine of the thing, so let me write this again, b of t negative x max. The sine of that angle is the vertical piece divided by the hypotenuse, but the hypotenuse is x max. Times omega. Wow. No way. That our velocity as a function of time wow, is just the y coordinate. Well, that doesn't, wait. There really isn't a y coordinate. That's, I mean, that's just cool looking and really makes me think about how much information is contained in this like platonic circular motion. But there isn't actually circular motion. It's just an idea. There's no y coordinate. We're just talking about motion back and forth. So this, wow, really neat, doesn't answer our question. If I tell you the x coordinate, can you tell me the velocity? But the thing is, this is a right triangle. So this y coordinate here, what if we represent it with the Pythagorean theorem? So we know that x squared plus y squared equals a squared, or x max squared. So if we solve for y, this thing, y is going to be either plus or minus the square root of x max squared minus x squared. Okay. So the minus sign here and the plus or minus here, those are kind of weird, but we're just going to have like a plus or minus kind of thing, or maybe a minus plus omega square root So if you tell me the x coordinate, I can tell you how fast you're going one way or the other, because you could be at the same x coordinate. We could be going to the right, we could be going to the left. We're not entirely sure. So at any rate, we know the size, the magnitude of the velocity as a function of space, not of time, which is what we said we wanted. Now let's see. We can make a little bit of a simplification here. Keep trying to erase with my hand. Makes everything worse. Equals, what if we factor out x max squared and then take its square root? So I'm suggesting this, omega, pull the x max outside of that, and then it's the square root of 1 minus x over x max squared. That's the thing we said was equal to v max. So we can modify that equation that we had a second ago. V of t is equal to v max times 1 minus x over x max squared. Wow. Okay. So we can say a whole bunch of things about velocity. What about acceleration? We need another derivative, and we wrote it a second ago. Acceleration as a function of time should be negative x max omega squared cosine omega t plus theta 0. And that's the whole story. Cosine of omega t plus x0, that's the x coordinate, over the hypotenuse. But then we're back to basically back to Newton's second law, relating that differential equation, the position, to its own second derivative. This is a special result, though. This is the result when our Platonic idea corresponds to oscillation. Anytime we ever get the result of Newton's second law to look like this, to have this kind of form, where we've got an acceleration that is negative proportional to the position itself, where there's some constant of proportionality, omega squared. Whatever that constant of proportionality is, this thing, this motion, we can model like oscillation, because this is the story. If this is true, then our circular motion Platonic idea is a good model for what's going on. Anytime this is the description of what's going on, it means that this is a model that's going to work to describe it. We talked about the maximum speed. We could also talk about the maximum acceleration. And it's just the one that happens when cosine is 1. So that's anytime we're on the rightmost side or the leftmost side. If cosine is 1, then we just have negative x max omega squared. So the minus sign is fine. The maximum acceleration is either plus or minus, depending whether we're being accelerated to the right or the left. X max omega squared. I'm sorry. Yeah, X max omega squared. Let's see. What else can we say at this point? We know that this kind of motion has energy associated with it. We've got velocities, so we can talk about kinetic energy. We've got a stretched spring, so we can talk about potential energy. When we initially pull that mass and let go so that it's pulled back by the spring, right at the instant we let go, it's not moving yet. Let's start the clock there. So let's start it so that theta 0 is 0. And we're going to start on the x-axis in our rotational system here. So our x coordinate in this case are, well, not r, but x max. X max cosine omega t. At that instant, we have stretched the spring. We've done some work to do that, and we know how much potential energy is stored in the spring right at the instant we let it go. The potential energy of the spring is 1/2 kx squared at all times, but in this case, we're talking about x max. So u at time 0 is 1/2 k x max squared. On our way through equilibrium, the spring isn't stretched at all. And none of the energy of the system is stored in the stretched spring, so it all must be kinetic as long as no other non-conservative forces are acting. And next week, we'll talk about what happens if friction is acting. But for now, let's assume that this is a conservative situation, so whatever potential energy we had, we should have that much kinetic energy on our way back through equilibrium. So kinetic energy at equilibrium should be 1/2 mv squared, v max squared, because that's when all the energy we have available to us is kinetic. None of it is stored. And that should be, according to energy conservation, equal to the maximum amount of potential energy that we had to begin with. Okay, so if we solve for Vmax, we gotta move m over this side, k over m, x max squared, take the square root, which is, we knew this already, because root k over m, that's how we decided omega would be, and the square root there, so it's x max, and that's the same formula we had before. This is great. Not only does it do the job, but it's internally consistent. We didn't start with energy, so like all of the different ways that we have to attack this problem all give us the same result. This is really, really exciting. How do these two things, the kinetic and the potential energy, relate at any old coordinate? Now, okay, so at any old x coordinate, there's generally some kinetic and some potential at some spot. I don't know where. But together, they need to add up to the total energy that we have in the system. We know how much energy we started with. It's 1/2 k x max squared. So the total altogether should be that. Whatever kinetic and potential we've got going on, they need to add up to this. Okay, fine. Generally, we're talking about 1/2 mv squared plus 1/2 kx squared, 1/2 k x max squared. Let's solve for v. We're going to move that one to the other side. Let's multiply through by 2. We've got k x max squared minus k. Well, let's factor out the k. X squared, divide through by m, and take the square root. We're back. This is the same formula we had a minute ago for the speed as a function of x. If root k over m, that's omega. And if we factor out the x max squared, we're back. This is the same formula we had a second ago. X max squared minus x squared. Well, and we took a square root, so I guess there's a plus or minus, exactly like we had when we were talking about position, velocity, acceleration in terms of the calculus. The energy gets us the same results. And that's the extent of what I'd like to cover of chapter 14 for this week. Next week, we'll finish chapter 14 and apply some of what we said about oscillation, periodic motion, or simple harmonic motion. And I want to just before we stop, I want to reiterate, I want to repeat that anytime we have a situation in which we can say that the acceleration is negative proportional to the position, the farther away from equilibrium we go, the stronger the system tries to pull us back. And that pulling us back, that's that minus sign. So if the acceleration is, anytime we bump into this, that the acceleration is negative proportional to the position, we've got a situation that we could model using our Platonic circular thing in the projection onto a screen. This is the condition for simple harmonic motion. Any other kind of motion we bump into, if we can write it this way, than it is simple harmonic motion. And that's what we'll do next time. Right? Thanks, everybody.